which states find the equation of motion. Position is a function of time for a charged particle q in the magnetic field that's in the z direction with the following initial conditions. Initial velocity as negative VOX in the x direction, 0 in the y direction, and VOZ in the z direction. The initial positions are 0 in the x direction, y not in the y direction, and z in the z direction. Oh no, and 0 in the z direction. So to start us off, I rewrote the equation of force by using a magnetic field and velocity of a particle, and this can be represented by this equation over here. This is just a cross multiplication of the particle speed and velocity cross multiplied by the magnetic field, which is traveling within. This whole function can be rewritten as this. This is when you solve for the matrix, and then you get this equation. And due to the magnetic field that we have, we realize that certain terms are going to cancel out. Like this term is going to go away. That this term is going to go away. And lastly, in the z direction, this whole term is going to disappear to 0 due to the fact that the magnetic field is in the z direction. So anything in the z direction will have to cancel each other out, or the magnetic field will not have any effect in the z direction because it is traveling in the z direction. So as a result, we are left with this bottom equation over here. To do this problem, I split it up into three parts. The first part, I'm solving for the position versus the motion of the charge in the y direction, and the second part, I'm solving for the motion of charge in the x direction, and the third part is solving for the motion of the particle in the z direction. So let's get started. So our first equation, so this is just I just rewrote mass times acceleration over here as mass times velocity dot Vx equals Vyb, and I'm missing a q over here, which is right down over here, so don't mind that first equation. Let's just look at the second equation. So that's a proper representation of what it is. So this from then on, I rewrote the same thing in the y direction. As you can see, in the y direction, though, we have a negative velocity, or we have a negative term, so that's how we do it. What I did is I used the second equation and I solved it for Vx. As you can see, Vx, when we solve for Vx, we have two terms in the right and left that depend on time, and they're different. So we cannot necessarily integrate this term to get the position in a certain time. So as a result, we had to do a bit of trick. So what I did next is that I integrated this part, and the reason why I did that is that I wanted to make this Vx to look like this Vx over here in the first equation. So what I did is I integrated, and this is what I got. When I integrate, since none of these terms depend on t, they become constant and they stay the same. The only thing that kind of changes is this Vy, and that becomes V double dot y. So the second derivative of y as a velocity or position in terms of time. From then on, I plugged this new Vx into the first equation that I had, and once you do that, so this is the first equation that we had, and I plugged it in, and this is what we need to plug it in, and I solve for Vy. And the nice thing about plugging it in is that you get rid of the x, so now you have two terms that are the same in both that depend on t, but are the same. So that works out very well. So what happens is qb over m, that is equivalent to angular velocity, so that we can just plug it in. And from this step to the next step, you kind of look at the equation and realize that this equation is just generally saying that uh, if I derive this equation twice, if I had the position, if I derived it twice, I would get the same thing with just a constant squared with a negative. Now, using logic, you can kind of infer that this equation can be represented as this, by this whole term. And from then on, once you kind of see that, you just plug in your initial conditions to kind of solve for C1 and C2. So we are given initial conditions in the velocity of y. We are told that at v initial, so when t is 0, the velocity of this particle in the y direction is 0. So once you solve that, you realize that when you plug in this 0, sine goes to 0, and cosine 0 goes to 1, so you have to C1 equals 0. Therefore, your new equation is represented with this term, this equation over here. So now you're going to figure out the position. And to do that, I just rewrote this again over here, and then I integrated. Now, when you integrate sine, you have to bring this. So you derive inside, and then what you derive inside with, you gotta divide by in the constant in front of the cosine, and then you gotta change the sign to cosine with the negative over there. But you should not forget that there is a constant in front because you're integrating. Once you find this equation, you plug in your initial conditions, and we are told that the y initial when t is 0 equals to y naught. So with that, we can figure out how these two constants are related to y naught, since we're given what is y naught, and we know that then we can see that C3 equals y naught plus C2W. So you can when you plug it back, the new equation, this is the equation of motion, position versus as a function of time for the charged particle in the y direction. So in the x direction, I did exactly the same thing. So when I realized that this equation over here looks like this equation over here, whereby the only difference is that I have Vy and over here I have Vx, I realized it's the same thing. So from then on, I did exactly the same thing until I got to plugging in the initial conditions. So we are told that when Vx at t is 0, it is negative Vox. So once you plug in those initial conditions, you get to realize that this is supposed to be C4, so excuse me for that. That C4 equals negative Vox. So once you plug, so C4 is supposed to be C4. So once you figure that out, you write the new equation, and realize that this equation is equal to this term over here. So again, you integrate and you plug in this you have a constant, and you plug in your initial conditions for x naught, and you realize sometimes will just go to 0, and you're left with this this constant over here, and then that's kind of gives you what C6 is equal to in terms of C5 over W, and the new equation will be that. The last part is pretty much easy. We are told that Vx has to be 0, and that means V is a constant, and we are told that that's V0 naught. So Vz dot is a constant, that means the velocity is V naught, or a constant. And from now on, you can integrate to find the position of the motion in terms of time, and you're given this equation over here.